Okay, good morning everyone. So I'm going to be up solving some open cup problems. I've basically been doing this for ICPC practice. And these problems are very hard, I think. But I'm going to start with an easy one. By easy, I mean it's has the second most solves. Doesn't I don't know how easy it actually is, but it's probably not too bad. Can I not copy paste in this chat? Um, so you're given two rectangles in an infinite 2D plane. Are they disjoint? Wait. Oh, wait. Hmm. What does it mean for the answer to be 4? Wait. So in this case, they're disjoint. So it's 3. Let me get out my tablet. This case, 1032. One zero three two 0123. I think these intersect, so it's 4. And then these two, they are the exact same. So I just need to have a way to check for any two rectangles. It's easy to check if they're the same. Check whether they're disjoint. So they're disjoint if okay, yeah, this is easy. They're disjoint if like the intervals span there are two cases. Either the intervals the x intervals of both of the rectangles are disjoint, or the y intervals of both of the rectangles are disjoint. Okay, so I guess it's like an easy warm-up problem. Probably shouldn't take more than 5 minutes. Okay, yeah, and I'll check the chat. I'll also open up a Jamboard just so I can write stuff for the next few problems. Okay. arvindr9 stream 6. YZJJ 3FT8. Oops, typo. Hello. Yeah, so I'm gonna code L. This is just an easy problem. You have two rectangles. See how many components it divides the infinite plane into, and you just need to check if they like are disjoint, or if they're the same, or if they just intersect partially. So okay. So if they're the same, then it divides it into two components. And my definition of disjoint, they can still intersect at endpoints, but they can't intersect anywhere else. Disjoint. So I'm just looking at the x and y separately. Uh, so two intervals. Oh, right. The silly thing where I can't name things y1. Wait, I have to name it yl. Wait, one sec. Was that the issue? Oh. What? Wait a minute. Am I missing a case? Oh, I'm missing a case where one rectangle is contained inside another. Because, um, in that case, like, the intervals seem to... Both of the intervals are contained in each other. Uh, so I might do something scuffed where this doesn't actually check if they're disjoint, or if they're disjoint, but it also um, looks for the case where one rectangle is contained in the other. Um, so these are just intervals for x intervals for rectangle 1, I x2 equals np r1 1 r1 3 iy1. That's not right. It's rectangle 2 0 2, rectangle 1 1 3. Oh, and it could also be 6 or 5. Yeah, I didn't foresee a couple of cases. So if they're disjoint, then... Hello, how do I draw? Oh. If they're disjoint, then we can label the components as 1, 2, 3. If they're the same, and then just one rectangle, so it's 1, 2. If they're intersecting, there's actually many cases. So if one rectangle is contained inside the other, then it's 3. Um, if they're like if they're intersecting like this or something, then it's 4. But there's like a bunch of weird cases. So there's like this 1, 2, 3. So you get 5 here, and you have this. There's like 6 components here. So this problem is low-key annoying. Oh. Yeah, you have all these weird cases. So yeah, this problem is low-key annoying. But these all depend on these 4 intervals. So I have to do casework on these 4 intervals. Um, so maybe I'll make this a bit cleaner. I'll make a function called calc. And then I have these 4 intervals, and I need to do casework on them. Okay. So let's assume they're not disjoint. So if disjoint ix1, ix2, or or disjoint iy1, iy2, return they're disjoint, then it's 3. And then we're also assuming that they're not equal. So the case we need to focus on is all the intersections. So if none of the intervals are strictly contained in each other, then it's going to look like this, and it's 4. And if exactly one of the intervals is contained in the other, then it's going to look like this, which is also 4. Like if it's strictly contained and it doesn't share any endpoint. Wait. Oh. No. I think every time if only one pair, there's only one pair of containment in intervals, then the answer will always be 4. So in this case, it's just these and these that are a containment pair. So let me just analyze patterns in the different cases. So in this case, this interval is strictly contained. So let this be R1, this be R2. This interval is strictly contained in here, and this interval is strictly contained in here. And to reduce the number of rectangles, we basically increase, like if the right endpoint of this and right endpoint of this are the same, then that will reduce the number of rectangles. But this is the case where you can match two pairs that are strictly contained in each other. So if only one pair is strictly contained, I believe the answer is just like, or if there's only like one pair of intervals, like either there's containment in the x direction or containment in the y direction, but not both, it intuitively seems like the answer will always be like 4. Given that they're not disjoint, because if there's containment in the x direction, it'll have to look like this or this, and there's no containment in the y direction, so this has to have some part outside. And then if same thing with y direction. So if only one pair has containment properties, then it's easy. If no pairs have containment properties, then it's going to look like this. So these are the easy cases. So the answer will always be 4 here. So we need to look at the case where there's containment in both directions. Yeah, so if one rectangle is strictly contained inside the other, then it's 3. So we need to look for the strict containment, or what should I call it? Oh, yeah, we need to look for the strict containment. However, if let's say that one rectangle in both intervals is contained in the other rectangle, but one of the intervals is actually equal, then this will create a new rectangle. So you see, this interval and this interval are the same. So it'll create a new rectangle. So this will be 4. So we can just name this length ix1, ix2, sorry, iy1. These are just the names of the intervals. ix2, iy2. So if ix2, I think we solved the case if ix1 is in ix2 and iy1 is in iy2, right? So it remains to consider the case where, so we have this case, I think we solved it. So the last case we need to consider is ix2 is contained in ix1 and iy1 is contained in iy2. So it'll look something like this, but with some variation. Yeah, so this is ix2. Oh, this is my pen. Okay. ix1, iy1, iy2. So this could range anywhere from like 2 to 6, right? In this case it's 6. So every time you have some endpoint that's shared, then it destroys a rectangle. So if these two endpoints are the same, then this rectangle won't exist. So you just reduces to check the number of matching endpoints. Okay, so let me code this. So since they're not disjoint, intervals are guaranteed to intersect. So it suffices to check containment properties. Okay. Just to make the code cleaner, I'll just change the condition to this: ix1 containing ix2, iy1, iy2 containing iy1. Just so it's consistent with this condition here when I code. Okay. And because of symmetry, I'll just swap things. So if iy1 dot first So here the answer can be 3 or 4, depending on whether one interval is equal. And then here I just need to look at the number of equal endpoints. Wait, no, I should have. Yeah, that's correct. Okay, this is kind of a lot for the second easiest problem in the contest. Disjoint. Oh, okay. Hang on a sec. Just gonna check something. Oh, it compiled. So close, but so far. So let's see what this 10320123 looks like. So I'm outputting a 5, the answer should be 4. So wait. Okay, yeah. Okay, for some reason I'm outputting 5. Okay. So let me test this case just by itself. L1. Oops. L1. So it should be in this section. None of them are subsets of each other. So shouldn't it be here? Okay, where does it return 5? So that means that it's this, for some reason this part is running. So for some reason ix1 is a subset of ix2, or yeah. Oh, I meant, yo, where is this 0 3? Oh, wait, no, I don't get it. Finding intersection of rectangles might give lesser cases, maybe. Um, although I don't know. I don't know how that helps to solve like this particular case, which is why I just decided to reduce it into. Oops, I'm drawing on the wrong screen, which is not touchscreen. Reduce it to like intervals, like 2 y intervals and 2x intervals. Oh, okay. I put R1 here for some reason. Okay, so this is correct. I could test this on cases, but I'm just gonna submit. Okay, I think I'll test on some cases. Um, mm, something like that. So I'll do like, or it's like 0 0 2 3, and then I don't know, maybe I'll make this a bit lower. So like 1. No, this would be 3 1, or 3 2, and then 4 5. 0, 0, 2, 3, 3, 2, 4, 5, and then I'll just put the expected output. So this should be 3, yeah, I don't think I've tried anything with 6, so I'll just put that as a case. 5, 5, and then 1. Can they be negative? Okay, I'll just do like 1, 0, 0, 1, 0, 2. So this would be like 4, 6. 1, 0, 5, 5, 0, 1, 4, 6. And the answer here will be 6. So let me just try with these two cases. Okay, that's not correct. Okay, so that means I have somewhere to work from. So x is a subset of y. Wait, that's weird. Oh, is x1 not a subset of x2? Make sure I type this right. 0, 1, 4, 6, yeah. Okay. Oh, I think I might have messed up again. So the point of swapping is so I can try to force x1 to be contained in x2. Let me try this way. I will run iy2. Oh, so initially we have that this 1 4. I mean this. Oh, so I just changed to 1 1 1 1 5 5 and then 2 0 4 6. Okay. I feel like I might be more confident in this code now because I just missed some cases earlier. Or I'll put in one more case, like this or something. Oops, keep drawing on the wrong thing. So 0 0 1 0. No. Forgot my high school coordinate geometry. 0 1 2 2 2 3. The output should be 4 0 1 2 2. Oh, before I try that, I'll just try swapping these two. Yeah, that's desired. And then 0 1 2 2 0 0 2 3. Yeah, and then if I just if I swap these, and then if I just try to extend this a bit, so it's 3 2, then I should get 5. Yep. Okay, I think I'm good to go. I mean, good to go doesn't mean I'm leaving the stream. I'll be here for another how many hours? I'll be here for another 100 minutes. But let's see if I can get this problem and move on to something. What? Okay, wrong answer in test 2. I think I might be getting somewhere now. Um, oh, I think I have an edge case in this part of my logic. So if it's like this, the answer is 3, but I'm outputting 4. I mean, yeah, like, because these intervals are the same, but it should be 3. So basically, if a rectangle is strictly contained, or if a rectangle is contained in another rectangle, the only times it will be 4 is if these intervals are equal and this interval is strictly contained in this, or the other way around. Okay. Let me try not compiling this, just making sure it makes me improve on that case. So this is, oops. Yeah, I was just talking about this case. This answer should be 3, but my program outputs 4. Like this case here. Okay, so let me name these coordinates. 0, 0, 1, 0, 2, 1, 3, 1. So 0, 0, 3, 1, 1, 0, 2, 1. Yeah, so it should be 3. So I'm defining some function for a strict containment. We'll strict p1, p2, that's weird. Is it not detecting that they're subsets? Oh, it is detecting, but what's the issue here then? Um, I'll send the link. Yeah, I've just been bricking on the same problem for this whole stream. I have to admit. Okay. One to strictly contained. Oh. Wait, yeah, that's correct. 4 is correct. Okay. Yeah, my initial answer was. Okay, so I just need to. Yeah. What I. Okay, I just messed up. I meant to put in this test case. So 0, 0, 1, 0, 1, 1, 2, 1, 0, 0, 2, 1. 1, 0, 2, 1. Yeah, and maybe there's a much more elegant solution. I don't know. I think my code for this is quite long. What? Wow. I'm surprised people are watching the stream, seeing me brick. But thanks for being here. Okay. Uh, Rip. I'm just gonna view test cases because I feel like I'm spending too much time on this. Enable coach mode. What the heck? Okay. Oh, is that why I have a wrong answer? Oh. Maybe my solution is correct, but I just had this random print statement. No. So 16th line, expected 4 but found 5. Okay, so I'm right on all these first 15 or so. Let me print out the 16th test case. T equals 1 or 0 T plus plus if T equals 16. Yeah, because like the way to usually debug these things, like if it's ask like it's like ask if it if it's like a problem that can be done naively, um, and it's expecting you to do a fast solution. The way you usually test these is we write a brute force that does the naive, and then compare the outputs on random cases. But I mean, I don't think there's anything like more naive than what I'm doing here. I guess technically I could do it on like small cases, and then just count the number of overlaps of each point. So that's probably something I could have done while debugging, instead of just coming with random test cases. So expected output is 4, but my output is 5. So let me mentally compress these indices so I can easily interpret what's going on. So I'm gonna perform a sorting algorithm by hand. Okay, this is weird. Like these are things I usually code things to do, but it's small enough that I can do it by eye. So then this will be 258 will be 3 2 1 2 3 4 5 6. Three. Wait a minute. Oh. It's 4. And then 2 0 5 4. Okay, so let me draw this. Wow, 7 people. People want to watch me brick. Okay, so let me draw this case here. Oh, I did indeed miss a case. I see. What is this problem? Wait, I don't think I missed. Wait. Okay, oh. So these two intervals are not contained in each other, and these two are contained. Um, I thought I covered that. Oh, I think. Hmm. Oh, okay. So I think my code treated that case just like how someone would treat this case. Like if you extend this a bit to the left, then it'll look like this, and the answer will actually be 5. See, I was only checking for equality of this and this, but I guess that's not sufficient because um, they're not equal here and they're not equal here, but this has 5 rectangles while this has 4 rectangles. So I need to check for something further than just equality. Um, so in my case, this is ix1, this is ix1, and it's a subset of ix2. Um, so I think it's safe to check for equality in ix. I need to treat the iy's a bit differently. This is iy1, this is iy2. Okay, that works. Okay, so compared to the previous submission, I'm better on on a test case. How do I open this? Does it? Okay. I spent more than an hour on this. Okay, what the heck? Wait, thought I'm in coach mode. Oh, um, wait, is this my most recent submission? No, it's not. So it's expecting a 4, but it's outputting 5. This is the sorted version. Oops. So then if I... Wait, is this a sorted version? Yeah, I think so. Are any two contiguous ones equal? No, they're not. So this will be 4, 5, 6, 7, and then 0, 1, 2, 3. Okay. And I'm outputting 5, but it's supposed to be 4 apparently. Let me look at this. Let me first run this. Oh, what? Oh, I think it's sorted in lexicographic order, which is not what I want. Maybe there's a setting. This is not even sorted. Like, this number is larger than this. Can someone sort this for me? Um, you know what? I'll just write a program to sort this. Oh, I can just write a Python program. Why didn't I think of that? What? Oh. Okay, so this should in fact be 1, 5, 3, 6, and then this should be 0. Wait, not 0. It should be 5. Wait, 0, 1, 2, 3. 4. No, this should be 1, 4. It should be 0, 4. 2, 7. Yeah, so it's getting 5, but it's expecting 4. So let me draw the input. 1, 5, 3, 6. And then 0, 4, 2, 7. I thought I covered this case. So it should not go here. Oh, let me read from the file. Where is it getting 5? Oh, wait a minute. Oh, yeah, I remember. This was the case. This is supposed to be the case where, um, like these are supposed to be the cases where both of them have, like, both x and y have intervals where one is a subset of the other. So in the other case, I would just return 4. Okay, that I took way too long. Literally half of my stream was, or there's more than half of my stream was on this problem. Okay, so let me look at D. And let me exit coach mode. I think I'll resubmit in regular mode. Maybe just clean up some comments. Oh, before I go on to the next problem, I'm just gonna look at someone else's code. How long is this? So this part is like a few lines, but I don't know, I guess it's kind of lengthy, but it's not too long, but I spent a lot of my time just like fixing bugs, like an extremely long time. Yeah, but I think in a real contest setting, I would like write a more naive solution, and then like the coordinates will be really small, and then for each coordinate I'll just look at for each coordinate basically I'll look at like where the boundaries are and do some kind of DSU or DFS or something. Okay, so let me look at someone's code. I'll look at SMax's code. Okay, this is seems way more elegant than mine. Okay, exactly coincide, that's easy. No overlap. Like disjoint. Okay, one contains the other. Oh, so the thing I was doing, if you're neither of these cases, I think I was doing something complicated, but either you have a star shape. I guess a simple way to think about it is either you have a star shape, in which case it's 6, or actually this is exactly what I did. It's like checking if these intervals have equal endpoints. But I think this is more elegantly written. And partial overlap is probably like this, I guess, where it'll be 4. Yeah, I guess it's the same as my solution, but it's written much better than mine. Okay, let's move on. Yeah, so I was working on H, but I've been like too lazy to code it, I guess. Also, like, I don't, like, I coded part of it, but I don't know if it's worth spending the stream time coding it. Um, like I was told it's like I read the solution is not that bad, but given that the solve count is 3, um, I don't know how confident I am that I can do it in the next 1 hour. So I might just leave this to some offline time. So I'm just going to try to make some progress on D. And I'd also read E. It's a geo problem that might also be of interest. So why does it say I didn't solve these? Because I coded this and I coded this, but it doesn't show that I solved these. Wait, let me look at my submission history. Call. Yeah, I've had a lot of submissions over the past few days. I think. Yeah, I don't know. Let me make sure my coach mode is disabled. How to enable coach mode. It's a special privilege you get when you reach. Oh, hi Shashwat. It's a special privilege you reach when you get candidate master. So maybe this will give you more motivation to practice. I don't know what your rating is in Codeforce, but um, if you want, if you one perk of getting candidate master is you can enable coach mode. So go practice. Um, yeah, but what coach mode allows you to do is actually I don't know all the details of what it allows you to do, but um, you can view people's submissions in the gym. Um, yeah, I honestly don't know what this is for. Um, like it doesn't give you. Wait, like can I just create a gym contest? Oh, I think I can create one. And if I disable, then I don't have the option. Okay, so I think coach mode is OP. I can create like trainings on the gym, um, and I can make the visibility public. So maybe this will, if you're looking for motivation to practice, this might give motivation. I don't know. Okay. Yeah, let me look at D. Oh, that's E. Yeah. Okay, so D. think I might ease a geometry problem, and usually these problems tend to have low solve counts because they delegate some person who's good at geometry. So E might also be doable. Um, yeah, so let me look at D. Wait, what is this asking? So K is fixed. So the answer to this is 2 because AA is splendid because you can duplicate K is 2, so it's like 2 duplicates of this small string A, and then BB is 2 duplicates of the small string B. Okay. And then here AB is splendid. AB occurs thrice. AB, no, that's not splendid. This entire thing is splendid. So I'm able to find 4, and then BA and BA are splendid. Okay. And K is small. That might be a key to the solution. Is this not just brute force, or does that not work? No, I think that's too slow. If K is small. If K is 2, then brute force might not work. Yeah, maybe this is something with suffix arrays, which I only know like vaguely. Since it looks like, or at least for K equals 2, um, you want to like count number of strings from each I such that these two are equivalent. And like the lexicographic representation of these suffixes will probably be pretty close to each other if they're equal. But I think this is a good string exercise, but I'm not good. I'd say I'm not good enough at strings to think about this on the spot. So maybe I'll go to the geo one. Maybe I'll think about D for a little longer, a few more minutes. Yeah, I think I'm not confident enough at string problems. So I'll look at E. Um, I thought about this for a little bit before. Um, okay, so for E, you're given some n m such that n plus m is at most 3000. Um, and you're given like n points, and then you're given like m more points. Yeah, I think I'll think about this problem for like 17 minutes, and then I'll spend the last 30 minutes trying H. So you have m points, and then you need to make like a spanning tree of each. So these are all embedded in a plane, right? So you need to make a spanning tree of each such that um, no two edges overlap, or like no two edges intersect besides endpoints. So something like this, for example, will work. And these coordinates are large, so like xi, yi is at most 10 to the 9. Yeah, so you need to make a spanning tree such that no two edges intersect. And these edges of the spanning tree must be straight lines. So you can't like circumvent something by doing this. Right? So is there a case where this is impossible? Um, it seems to be possible in many cases. Like maybe something that's super adversarial is like this. I don't think it's possible here, um, because this edge has to cross through here. Oh, no three towns are on the same line, so you'll never come with this kind of a thing, right? Um, Maybe it's always possible. Hmm. I can't think of an algorithm to do it, but maybe like suppose at some point that you're trying to connect like these are in two different components, and you want to connect these two components, um, but like for every for every candidate edge that connects those two components, it crosses through some edges that are already created the other color. Something's making me wonder if there's some kind of bipartite problem, just because there's like two sets, but oh, okay, I think I found a case where it's impossible. So basically, oh, is that also an impossible case? Let me look at that. Black 00, black. I'll do the chat from this PC. Black 05, red 22, No, that works. You can just connect this and then connect that. But I think this case is impossible if I have like exactly two red points and then um, I have two black points. It's obvious that it's not possible to um, so like since it's 2 points, these two red have to be connected by this line segment, but then it's not possible to connect these two black points. Um, so basically, and this also works in general, or it's not full generality, but slightly more general than two black. If you have like a cluster of black points here, you have a cluster of black points here, then none of them connect to each other, um, or like every edge that connects one of them to the other has to pass through the um, red one, then it doesn't work. Oh, sorry, did I? Oh, I'm at the wrong screen, my bad. Um, yeah, so this case doesn't work. I mean, this case works because you can just connect black to black, red to red. But what I was saying is, if you have like two reds here and then black here, and then not the spanning tree for the black has to has there has to be some edge connecting this component with this component, right? But there's no edge. There's no This red edge has to exist because there are only two vertices, so there's no such edge. I think you can also like say that's the case if if you just have a bunch of red points here and black points here and black points here. So this must be connected, so it'll obstruct the path from this component to this component. It'll obstruct any path from this edge from this component to this component. And then if you add like some extra vertex here, then you can make it possible. You could potentially make it possible because you just use this as a connector between these two components. Oh, sorry, I forgot this again. Yeah, so basically if you have a bunch of red points in the middle of the black points, oh, then like you can't use anything here to connect this to this. But if you add another black point here, then you can connect it. Oh, your example was yeah, that works. So I mean that's invalid. So yeah, that's a counterexample. 0050. Oops. 0050 and then 222 -2. Technically, you can't have three collinear points in the input, but is my tablet okay? But if you have if it's like this, then yeah, it's invalid for the same reason I talked about here. Maybe this motivates some kind of greedy algorithm. Like process the points in some order and then try to connect it to something, because yeah, I'm not sure, but like if you process this point up here last, um, and then just restrict to these points, then you could connect these, then you can make a component out of this, and then you can make a component out of this, and then when you process this last, you can connect these two components. But it's not clear if a greedy algorithm works, and if so, like how I should order them. Convex hull, maybe. Yeah, I mean convex hulls tend to have a good deal of structure, and they tend to um, simplify things. Um, Maybe that might be of use here. Oh, maybe like something one might be able to guess and try is, you have a bunch of black and red points, right? Let me move to the next slide. You have a bunch of black and red points, right? Um, so what I observed earlier, like I have no idea if this is the right approach, but what I observed earlier is that if you have like a faraway black point, and um, like it could serve as a connector for components that seem to be like not connectable earlier. So I mean, this kind of suggested like maybe processing the inner points first and then going toward the outer points. So maybe one thing like someone might be able to guess is, you have all your points, just take the convex hull of everything and then recursively solve on whatever is strictly inside the convex hull, um, and then consider your convex hull and try to connect it with points. So solve this for this and then connect points that are on the hull. Again, it's not clear exactly, like there's certain questions like first of all, I have no idea if this even works, and then the questions like, which point should I look at first, and then another question is like, when I'm connecting to here, should I change any of the edges that are inside this, inside whatever I constructed here? Yeah, but I think this is a good start, maybe, or ideal, unless the solution is something completely different. Okay, I have 30 minutes left, but I think it is a good opportunity to think about some problems. I'm gonna try coding H, which I've been procrastinating. So I'll explain what H is. So you have a bunch of points, or you have like up to 5,000 points in a 2D plane bounded by 0 and m, and you have a bunch of query points, and for each query point you need to calculate the largest square that contains the query point that doesn't strictly contain any other points. So wait, okay, good, I'm recording. So H, you're given a grid from 0 to m, like coordinates are from 0 to m, and m is at most 10 to the 9. And you're given, there's a bunch of points on this grid. So n at most 5,000 points, and then you have q queries. I think that's also at most 5,000. Yeah. So given a point, the query asks, given a point x, I, y, find the largest rectangle that strictly contains this point, and does not strictly contain any other points. So in this case, if I look at this rectangle, I might be able to make it larger because there's some empty space here. So instead I will choose like this rectangle, and this rectangle has to be completely, sorry, not rectangle, square. The square has to be strictly inside the 0 to m region, or not strictly, it can also touch the boundary, but none of the other points should be strictly inside it, and then this query point should be strictly inside it. Okay. Now one observation for this problem is that if you look at an optimal solution, you can move it to the left or right such that, like, if you have an optimal square, then there exists an optimal solution where either the left point or the right point shares an x coordinate with one of these black points, right? So in this case we're already done, because this point shares an x coordinate with this point. But suppose not. The thing is that like you can keep shifting it around. You can keep shifting the square around. If you don't touch any black points, then you can enlarge the square. And then you can also consider this boundary as a black point or something. It doesn't change the answer. Then if you shift this around such that this point is strictly inside, and you don't touch, you don't you don't share any x coordinates with any of these black points, then you can enlarge the square until until either your left side or right side shares an x coordinate with some black point. So I think key observation, I don't think I'll have time to code this, but I'll try to code a little bit. Observation, there exists opt solution where some left or right boundary has x value xi for some point pi. So we're just assuming we label this as p1, p2, p3, p4, right? Yeah. So you can basically do this problem in O of q times n squared. Just deal with these two cases separately, right? So just deal with the case where the left boundary has the same x coordinate as some point. And then when you fix a left boundary, then just like look at different candidates for like how long the side length will be. It will depend on like the locations of everything else. So if we fix a left boundary, like computing the candidate sizes of the square will be O of n. But actually, one thing to notice is that if you move your left boundary to the right, then the right boundary will also go to the right. I'm being very vague here, but you basically, because of these constraints, you want to speed this up to O of qn, right? Oh, does convex hull fail in that example? Let me pull up Desmos. Wait, can you plot things in Desmos? Like different colors? I don't know. I'm gonna think about that in my back of my head. Yeah, but I don't know, if we like, we can feel free to talk about this in Discord, like some of these problems in Discord. I think some of you probably know about this because I advertised this in Eric To official server, so we can discuss this there. I have 19 minutes left in my stream, so okay. So let me do a bit more drawing stuff. It's actually hard to explain. So if you have a query point here, and then this is like your entire thing, right? Coordinates are from 0 to W. And just consider the case where left boundary of the square has same x coordinate as some pi. So so when I add this point here, this basically rules out. So over here, I basically have that the left boundary can be anything here, up to constraints that are imposed by points that are later. But when I see this, when I add this point here, and I want to push, if I want to push the left part of the square farther than this point, then the interval where the left boundary of my square is restricted to here, right? Because if it's outside of this interval, then like if it's not contained in this interval, the square has to contain this red point, so it'll strictly contain this point, so that's not allowed. And then when I add a new point, then the interval gets restricted even further. So note that these intervals where I can have my left boundary of the square has some kind of monotonic structure. So as I increase x, it basically gets like, it gets larger. And then at the same time, the right endpoint, as I move this to the right, then the right endpoint of the optimal square increases. That's the high level idea. So I guess for implementation, oh sorry. So what I was saying is that in the beginning, or not in the beginning, but if the left boundary, so we're just considering the case where the left boundary of the square has the same x coordinate as some one of these points pi. Yeah, so we can just say there's a point here or something. So if the left boundary is here, modulo constraints imposed by points to the right, our left boundary can be anywhere in this interval, so it can span the entire interval unless there's some points that constrain that. And when we look at this point, then the left boundary can't extend above this because it has to contain this red point. It'll imply it'll contain this black point. So the left boundary has to be in this interval, and then as we go to the left, these intervals get more and more contained. So basically, as you move the left boundary to the right, the candidate locations where you can put the left boundary, it's like a superset of the earlier candidates. And then when you move the left boundary to the right, you can say the same thing about the right boundary. Like it basically increases. You can see this is true because it doesn't decrease, right? Because if there's a square here, looks like a rectangle, just pretend it's a square. You know that for later left boundaries, this right boundary is feasible, right? You can just, so this is the first left boundary, this is the second left boundary. Let's say this is optimal for the first one. For the later left boundary, this right boundary is still feasible because it's just contained in the earlier left boundary, right? Okay. So in order to compute all these intervals, you can think of these points as adding an extra constraint, like y less than or equal to c1, y greater than or equal to c2. So you can basically store all these intervals in the stack, just process them in order from right to left, and then when you're moving forward, you basically pop from the stack to see where all the candidate left boundaries are. And then you can do a similar thing with this right hand side. Yeah, so I only have 10 minutes, so I don't have time to code this. I want to code this. I tried to code this a few days ago, but I got busy with something else. Maybe I can start coding this. Or if we want to discuss something else, maybe we can look at E for a bit. I'm actually curious about E, where a convex hull fails. Yeah, so I guess this particular stream has mainly been like, I was intending it to be me solving problems, but these problems are kind of ended up running into bugs, and some of these problems are kind of hard. But I personally feel this is still like an interesting discussion, especially problem E. So let me look at the case you're talking about for E. Yeah, but if you have any suggestions for future streams, what you want to see, sure, let me know. This is kind of me trying to motivate myself to look at these problems that I was doing for some ICPC practice. Okay. Technically, these coordinates have to be greater than or equal to 0, but I don't think that matters. I don't think that changes anything. So let's see. B is 0, 0. So black is 0, 0. Two, 0. 7, -2. 5, -4. 6, -8. I'm making these super approximate. 10, -8. Oh, I miswrote. Okay, so these are conveniently sorted in x. Oh no, they're not sorted in x. I was correct. Okay, R has 2 points. Let me draw that first. 7, -5, 10, -3. Wait, 7, -5, 10, -3. So, oh yeah, that's the same x value. So let me just write this. 6, 7, 10. 5, -4. Okay, I'm just gonna an online scatter plot. Okay, this is much more. Zero, 0, 2, 0, 7, -2, 5, -4, 6, -8, 10, -8, 7, -5, 10, -3. Wait, did I miss some points? Yeah, I guess directly using convex hull fails because the 6, -8 point and 10, -8 point are on the same hull at the end. But maybe it might still, like, we might still be able to do this convex hull technique, but so I guess if we use convex hull in iteration 1, we're just processing these 2 points, 5, -4 and 7, -5, and if we solve for them, like, we don't have to add any edges to connect them. And then we're adding this new convex hull. Is this even convex? Oh, I see. Oh, I see. There's like, oh, okay. So the convex hull of the entire thing excludes this point. So actually, yeah, convex hull of the entire thing excludes these 3 points, and you connect an edge here, and then when you look at the final convex hull, we'd have to connect this here first, and then connect this to here, and then you have to connect these 2 points to each other. I don't know. It's hard to decide. I don't know how to decide like when to connect 2 points. Maybe like there's some nice property of like the Euclidean plane where if you connect like the minimum weight edge, then it has nice properties, but I'm not sure. Or connect the maximum weight edge. By weight edge, I mean like the distance. Oh, you might want to connect the max weight edges at the end. Or like have some kind of priority for connecting farther edges later. Just because of the example I showed earlier where you have two black components um, separated by some long red edge, and then you like connect the and then there's like a black vertex really far away, and you connect that at the end. But I'm not entirely sure. Maybe you can do something in parallel, like if we're saying that, let me go back to this board. I have 3 minutes, so I'll have to drop off soon, but I was mentioning something about possibly wanting to prioritize longer distances for the end. So you have like this long red edge, and then you have a bunch of black edges here or something. Oh, I shouldn't connect them yet. You have something like this, and then you have black, and then you have this thing that's super far from all the other black ones. So I was thinking like maybe the order in which you process these are like an increasing order of distance. So you connect this first, this first, this first, this first, until you have two components, and then you connect these. And then what I was saying about doing it in parallel is that let's say these two red things are very far, then you might accidentally end up connecting two things from here, and then you can't connect the red. But maybe something in parallel would be more effective. So find the smallest edge between the black, and then just alternate between connecting black and red, then find the smallest edge between red, and that will guarantee that you won't connect anything from here to here. Like you won't, yeah, it'll guarantee that you won't have an edge like this if you connect this red thing early enough. So maybe alternate between black and red, or have some way of like prioritizing that each color gets connected early in the stage. But yeah, I think there's an interesting set of problems. I didn't really solve anything, but I think it was interesting to think about nevertheless. Feel free to just feel free to reply to my blog post in Codeforces. It's a nice, interesting 2.5 hours. Thank you.